Yeah, thank you, Ken. And thanks, Cruz, for hosting. I really appreciate it. Yeah, and thank you, everyone, for coming. And everyone can hear me? Cool. OK, so the name of the talk is Scavenging for Reusable Code in the Kubernetes Codebase. And I wanted to give this talk because I had been writing Go for about 4 years. But sometimes it feels less like programming to me and more like scavenging, like running around in the dark trying to figure out what I'm trying to do, especially when you get into much larger code bases. So I wanted to kind of give you some of my techniques for doing that, and then see how it's applied to kind of the projects that I work on. And in fact, I was originally going to call this talk Roadside Picnic, which is the name of a Soviet-era sci-fi novel. And in the novel, it takes place in a world where aliens have come to Earth and then left, and they've left behind a bunch of this alien technology. And the technology is very sophisticated, but it's incomprehensible to humans, and some of it is really dangerous. And so the governments of the world have quarantined it into zones. And then there's a whole industry of scavengers in that world who make their living by dangerously making excursions into the zones, finding technology, and bringing it back. And this is how I think about the Kubernetes code base. Like, there's a bunch of like really, really amazing stuff in there, but like I don't really understand all of it. And maybe I have a few waypoints and markers, and I can get in and get out and like not hurt myself, hopefully. But I'm not an author of Kubernetes, and I didn't write the code base, don't have sort of full comprehension of it, but I'm still able to use it to my advantage if I use the right techniques. So that's sort of what I want to talk about in this talk. Cool. OK, so a little bit about me. I'm a software engineer at a company called Buoyant. I've been there for 4 years. Prior to that, I was at Twitter for 5 years, working on the platform team. Buoyant builds infrastructure software, and specifically we have an open source project called Linkerd, which I will talk about in a moment. I'm also a member of the LGBT community, so I'm really interested in promoting diversity in tech, and would love to talk to folks about that at the break if you're interested. And yeah, I have a lot to cover. I've also given myself a really impossible task, which is to talk through somebody else's code base in presentation format and like put a lot of code up on the screen. So I might move a little quickly, and hopefully it's comprehensible. But yeah, here we go. OK, so the first thing I'm going to do is talk about Kubernetes and the Linkerd project and how they relate to one another, and why it's a good idea for Linkerd to leverage a lot of the code from Kubernetes. Then I'm going to give you sort of my outsider's perspective on how the Kubernetes code base is laid out. Spoiler, I don't have a good perspective on that. And then I'm going to go through 2 examples of how we've kind of gone through the code and found things to use, and then just wrap it up. So any scavenger needs some really good tools. These are the tools that I use when scavenging. First, I'll check out the code. I will like grep for it intensely, for things that I'm looking for. When that doesn't work, I'll turn to Google and search furiously and end up on GitHub sometimes. Oftentimes, I'm like taken to the Go doc and try to figure out how things work. And then the last one, go run test go. What I mean by that is another technique that I use pretty often is when I'm trying to use something from a code base that is not mine. I'll write these throwaway scripts to kind of experiment with using them in isolation before I try to incorporate them in the project. And it's good because you can iterate really quickly and kind of get a handle of like what these things do. OK, all right. So let's just talk real quick about Kubernetes. I know we're all Go fans. Kubernetes is a very, very large Go project. Some of you may be familiar with it. Linkerd is also a large Go project. They're both in the Cloud Native Compute Foundation. Kubernetes is a container orchestration system. All that really means is it helps you run a bunch of Docker containers on a bunch of nodes. And it's massive. It's like a really big project. Just in the root repository for Kubernetes, there's over 350,000 lines of Go code. There's an enormous community. Linkerd also has a very large community in the Slack channel. So I'm going to tell you a little bit about how Linkerd works on top of Kubernetes, which will help to understand the examples that I want to give. So let's see. When we talk about Linkerd, it all runs in Kubernetes, but we typically talk about it as the data plane and the control plane. And so the data plane is running right alongside your existing application. So if you've deployed your application to Kubernetes, you would have these tiny little proxies sitting inside your container pods or on your pods in Kubernetes, and they would be receiving all inbound traffic to the container and then sending all outbound traffic. So they sort of are these intermediaries that act right at the network edge for your pod. And those proxies are written in Rust. So I actually work with quite a few people who love Rust. I think people that love Rust almost as much as people who like Go. But that's sort of the part that sits right next to the application. And then the proxies are completely controlled by this control plane that runs in a different namespace. That's entirely written in Go. It's pushing configuration down to the proxies and then pulling performance data and metrics data back out of the proxies. So you get a lot of visibility into how your traffic's performing, and then you get a lot of ability to configure that and sort of reroute the traffic on the fly, that kind of thing. But yeah, pretty much everything in the control plane is written in Go, and I'm going to focus on two areas today. So Linkerd has a CLI, which is command line interface. It's very similar if you've interacted with Kubernetes. Kubernetes has the kubectl command for controlling Kubernetes, and we have a binary called Linkerd, which you can run. And those two tools work together, as we'll see. And I'm going to talk about the tap server. So another really cool thing that Linkerd can do is once it's routing all your traffic through the proxies, you can actually just tap into like a live stream of requests and get back a bunch of data. And we augment that data with data directly from Kubernetes. So we have to look up a lot of metadata and that kind of thing. So tap server is kind of constantly pairing these two data streams together and then sending it back to the client. But anyway, that's all I'm going to say really about the specific Linkerd. It's a great project. Check it out. I brought T-shirts. They're on the table over there if you want them, and stickers. But yeah, let's see. But really, this talk is about Kubernetes and how we can sort of find useful stuff within Kubernetes. So here we go. So you would probably start at the root of the project in the main Kubernetes repo. I think if you ls it, it looks something like that. There's kind of a bunch of things here, but fortunately, it looks kind of like a standard Go project. There's at least a few similarities. One is that it has a CMD directory, and that's where they put all of the mains. So sort of all the different processes that Kubernetes has to run to schedule containers are the main methods for those live in the CMD directory. And then similar, as a parallel, they also have a package directory, and that's kind of where the libraries live that back up the mains and like provide most of the functionality. And I think that was the original project layout. But over time, it got bigger and bigger and bigger. And eventually, there was a decision to take some of the reusable parts of the project and split them into separate projects so they could be used in isolation. And that is kind of what's going on with the staging directory. So my hypothesis, although I don't actually know how this evolved, is that in order to kind of keep a single build, like a mono repo style build, a lot of the independent projects were moved within the repo to the staging directory. And then when Kubernetes releases are cut, they will publish all the projects from the staging directory out to their separate repos. And then other developers, like my own project, can depend on the projects individually, but they all kind of get developed within this repo. So if we look in the staging directory, there's like a lot going on there. These are just a bunch of different projects. They do lots of different things. They can be run in isolation, but they often work really well together. And then there's also a whole set of Kubernetes projects that were developed outside of the main repo too and are now dependencies of the project. So you can find them at the kates.io root to import them, but they don't come from the main Kubernetes repo. So that's sort of this batch. But this is like a lot of code to go through. So in this presentation, I'm really just going to focus on the packages that I know and love. So CLI runtime, that's really important for Linkerd. Since we have a CLI, Kubernetes has a CLI, we can share some of that code. Client Go is this like very robust package for talking to the Kubernetes API, and it has a lot of stuff in it. And then let's see, API and API machinery are projects. Like one holds the API definition itself. The other one is a bunch of utilities for working with the API. And then we also use sort of a bunch of other random projects, but I won't get to those as part of this talk. Okay, cool. So here we go. We have our first mission, the first scavenging mission. This one's pretty simple to understand and hard to know how to fix. So here's the simple premise, which is this is a really common pattern. So when you want to run stuff on Kubernetes, you would have a YAML file with a bunch of YAML objects in it, manifests. You apply that to your cluster, and then Kubernetes takes over and sets them all up and runs them for you. So, and in the way that Linkerd works, by putting a proxy next to all of your containers that are running is we call that injection. So we would actually run Linkerd on the YAML file first, and it will add the proxy YAML next to all of your existing containers. And then when you pipe it to kubectl to apply it, all the containers spin up, and they also have the proxy embedded in them, which is a good pattern. And so this is something that people sort of do all the time. They take Linkerd to inject the YAML, and then they pipe that to kubectl to apply it. And so you can see that the first 4 lines here are from Linkerd. That's sort of its output while running its injection. And then the next 4 are from kubectl running the apply. But they don't look the same, right? Right? They're trying to communicate the same data about the objects, but they're not formatted the same. And this drives me crazy, right? Like there's somewhere in the Kubernetes codebase that mashes these strings together, and we're like mashing them together in a different way. So like, it's kind of a trivial example. Maybe we can try to find it and fix it. We'll see. Okay, so this is the part of the presentation where there's gonna be a lot of code and a lot of red arrows, and I'm gonna talk really quickly, but hopefully, like I said, hard task. Hopefully it makes a lot of sense. But here we go. So the first place that we will look is in the kubectl command package, which is not actually in the command directory, it's in the package directory, because it's the library that supports the kubectl command itself, which is how they produce the kubectl binary. Whew. Get ready. All right, so kubectl uses a really cool library called Cobra, and Cobra is useful for configuring command line utilities. What's really nice about it, and so you return a Cobra command object, and then it works. What's really nice about it is that it uses nesting of commands. So you can have a root command, and then you can have subcommands, and the subcommands can have additional commands, and you can have configuration and flags applied like at the root or at the subcommand or any additional subcommands. Has really good validation. You can take arguments, stuff like that. So Kubernetes or kubectl uses that, and Linkerd uses it as well. And so you sort of have to produce this top-level Cobra command in order for anything to work. But we're really interested in the kubectl apply command, apply being a subcommand of kubectl. So if we instead go to the apply package, then we'll see a new command apply function, and it also returns a Cobra command. And so this is sort of the meat of what's executing when I run kubectl apply. So I think we're in the right place. It returns a Cobra command, and it has a run function. So when you apply something, it's really just executing the code that happens inside the run function. So let's see how we build this command. So the first thing I would do is kind of look at the arguments that are passed in to how the command is built. It runs. And one of them is this factory object. So at this point, I'm like, okay, well, I need a factory in order to build a command. So let me see if I can try to understand that. And I click to the factory in the util package, and I see this. And I am sure people understand this. I do not know what they're saying at all. Like this is sort of a dead end for me because like the rings here are for a reason. I don't know. So at this point in my scavenging, I kind of back away. I'm like, well, maybe this isn't going to tell me how strings are formatted. Let's go back. So I'm back here, all right, right? But we still have this function, and the very first thing the function does after it's configured is it creates a new apply option struct, right? So, and if we look at new apply options, it's pretty straightforward. And Go initializer, you call it, you pass it some streams, and then you get back an instance of the apply option struct, right? And then in new command apply, we like in the run function, we actually eventually call run on the option struct. So we built the option struct, then we're ready to run it, and this is sort of where I expect things to kind of kick off. And so sure enough, the run function does a lot of stuff. I actually think this run function is like 300 lines long. Like it's a beast. But eventually, it has accepted this file input. There's a bunch of objects, and it uses this visitor pattern to go through all the objects. And then after it's processed an object, it prints some information about that object. So if you scroll way, way down, here's the visitor pattern. And then it eventually creates a printer from the option struct by calling toPrinter on the option struct. And then it calls printer.print object, and that's what produces the strings that we see on the command line. Okay, so where does toPrinter come from here? It's a function on the option struct. So it turns out when you configure an option struct, there's a pattern throughout all of the subcommands, is that they have this complete method that kind of fleshes out the options before you're ready to run. And so you can see that it's in complete, it has toPrinter defined as this function, and the function eventually we'll reference the print flags field on the option struct and then call to printer. And that seems good. But what are the print flags? They're here in the new option struct. And in there, the print flags are being configured via a different package called generic CLI options. And so at this point, we kind of like scrolled up and down in the apply code a lot. And we're going to jump to the other package, generic CLI options, to kind of see how that's configuring the printer to see if we can find anything that will help us print strings. All right, so we move to generic CLI options. This is where the print flags come from. You can see that it sets this output string to empty string. And then it returns the print flags. It has a few fields. One of them is called name print flags. And I'll just clue you in that when Kubernetes prints those strings, it's called name printing, and it's not JSON printing or YAML printing. That took a while of scrolling around, but I don't want to go through that part of the journey. But we can see what the name print flags look like. So that's really just a simple struct that has an operation, which is the string that's printed after the object. And it supports a toPrinter method. So this is sort of all the way from the apply code. We're calling this print method. And the first thing it does is it checks its output format. And it turns out when it was configured in this way, the output format is empty string. And then it calls toPrinter on the name print flags, which we know are initialized based on looking at the initializer. And then name print flags has its own printer here, and it parses the output format, and then it eventually falls through and returns this name printer. So it all kind of fits together, but at the end of the day, you get back an object. That object can print names. So let's look at the name printer. I think we're getting really close. So name printer is an implementation of resource printer which outputs resource/name pairs of an object. So I think we found it. Basically, like this is the thing that does the printing, and we just have to kind of inspect it to see what it does. Yeah, the operation for the name printer is the string that follows. You know, it's the thing that took place on an object. And if we look, it has a print object function, which calls that's a publicly exported function, which calls a private function called print object. And if we look at private print object, then we can see that this is actually where the formatting of the strings happens. They're using printf. If the resource that you're printing belongs to a subgroup, then the subgroup is printed. But basically, this is kind of where it's all happening. We're sort of far from where we started. We're way down in the CLI runtime project and the printers package, but we found it. And we can fix it. So actually, when I loop that code into the Linkerd CLI and run it, when I pass it the objects, it spits them out like this. And we've sort of been able to rip out the code that we were using to do it kind of incorrectly and then go back to the way kubectl is doing it. OK, so that was like a journey, right? We went a long ways there. It may seem really silly, right? Like to spend all that time when you really just want to format some strings. But overall, like our goal is to really simulate the look and feel of kubectl. So the more we can leverage from the Kubernetes Codebase to do things exactly the way the kubectl does it, then the better off that we are. And I have an additional point, which is I'm going to call bonus loot. So through our excursion, we've kind of done all this scavenging. We can kind of take a few other things away. So by looking at that generic CLI options package, it really does two things. It configures printing, so that basically controls the output of the command, and it also controls cluster configuration. So the kubectl command has to talk to a Kubernetes cluster, and that requires a bunch of credentials and authentication. And you have to have a config file, and that's parsed, and then there's sort of token exchange that happens and all this stuff. And that's actually a lot of code that's in the Linkerd Codebase to talk to a Kubernetes cluster. But it turns out we can hook our client up to the config flag parsing and build Kubernetes clients in a lot more streamlined way, and also have them support all the types of authorization and everything else without a lot of manual work. So this is sort of like a bonus that we get if we just adopt the CLI runtime package. Cool. Yeah, there we go. It builds REST clients that you can use to talk to the Kubernetes API. And so that's how we can talk to the Kubernetes client now with a lot less configuration in our own code, or Kubernetes API. Cool. OK. All right, so we're just going to keep going. There's a lot more to cover. I have another mission here, the thrill of the hunt for pods by their IP address. Basically, the basic premise here is that when Kubernetes deploys your containers, it will typically put them inside a pod, and then that pod has to be reachable, so it's assigned an IP address. In the same way that code running on a physical machine may have an IP address, all of your code running in Kubernetes is findable via IP addresses. So Linkerd, which is really a router, is often concerned with IP addresses, and often what we want to know is who owns this IP address, right? Like if I have an IP address, which pod or which deployment is that actually pointing to? And so in order to do that, we have to kind of look things up in the Kubernetes API. In this example, I'm going to sort of take the script approach where I'm going to write a very simple script to find pods by their IP address, and then we'll improve it from there. And then just know that at the end of the day, once the script is ready, we can use that in our own code base, and it'll be good. Okay, so the good thing is here we're working with the Client Go project, which is one of the Kubernetes sub-projects. And Client Go actually includes examples. So there is an examples directory, and then within there are a bunch of different examples. So you can kind of find one that works for you. So we're going to start with their out-of-cluster client configuration example. Here it is. It's just a main func that runs through calls the thing. So the first thing it has to do is build a config to talk to the cluster. It basically has to parse your local config. And then with that config, it has to build a client, which is the next thing that it does. And then once the client is ready, it can call the endpoint that returns all the pods. So with the client, you can just fetch all of the pods. And then if you want to find, and then in this example, it just prints the total number of pods in the cluster and exits. So this is sort of our starting point, right? Like this code already exists. We were able to find it through the examples directory, and we can modify it pretty readily to find pods by their IP address. So that brings us to our first attempt, which is the list all pods approach. So we're doing the same thing, right? We have a main, we parse a config, and then we build a client. And then we list all pods, and then we loop through every single pod and check to see if its IP address matches the IP address that we're trying to find, and if so, then we output the pod. I'm going to give this approach 3 frowny faces. This is not a good way to find pods by their IP address. It has a lot of deficiencies. One of them is that you have to look up every single pod in order to find one of them, and then you have to walk through every single pod serially before you get to the one that has the IP address that you're looking for. So we can do a lot better than this. It turns out we can do a lot better with just the primitives that the Kubernetes API gives us, because they offer, for every resource type, they offer a list endpoint, but they also offer a watch endpoint. And watch endpoints will not just send you the whole list at once, but they will send you updates when the objects are created, updated, or deleted. And then you can use those to kind of build your own map of the state of the API in memory, which you can then reference when you need to look up something by IP, and you don't have to make an additional API call and then pay the cost of parsing everything from the API. So we'll just move immediately to the watch all pods approach. So kind of similar to what we did the last time, but we need some sort of data structure to store all the pods in memory. And this is really just a simple map, right? This is a map of IP address to pod object, and it has a mutex, right? So we need to be able to write things into this index and then pull them back out. So I called it pod index. It has a setter and a getter, and that's really about it. When you need to put a pod into memory, you lock it, put it in, and then you can read it back out. And that way, when you need to find by IP, you just look here. Okay, so this implementation looks a little different, right? So first we create our pod index, and then we call the watch endpoint. And then at that point, we spin up a separate Go routine that's constantly populating the index based on the watch events that it's receiving from the watch endpoint. And the watch endpoint just streams these endpoints back repeatedly. So every time it gets a new pod, basically every time there is a new pod that's created, it will take its IP address, put it in the in-memory map. So the script starts, it kicks off this indexer, and then the next thing we do is we sleep for a second. And we sleep for a second because I don't know how long it's going to take to really build that index of all the pods in your Kubernetes cluster. Like if you have 10 pods, probably very fast. If you have 10,000, I can't really count for it. So, my script just guesses that probably a second is going to work, and then we proceed, right? So, and then at that point we say, okay, now when I want to find by IP address, I just read from my pod index from the map and return that. So way more efficient. A few deficiencies. I'm going to give this one 3 neutral faces. I feel like we can do a lot better, especially the sleep and not really having any notion of whether or not the index is correct. If it correctly represents the actual state of the API is problematic, right? Like if you weren't processing the events properly, then you might, your index may become corrupted and you have no way of reconciling that with what's actually in the API. And anytime you're sort of creating a local cache of like remote data, you need some sort of reconciliation process to make sure it doesn't get in the way. So at this point in the development, and we were doing different things like this in Linkerd, I would turn to my scavenging tool, Google, and just start searching around for how do people cache client Go responses. And then the first thing you're going to find if you do that is the cache package of client Go. And that seems like the right place to be. So go ahead and click through. Package cache is a client-side caching mechanism, and it's useful for reducing the number of server calls you'd otherwise need to make. This seems like the right place to be. But it's a little hard to read the Go doc here. So the next thing it says is, Reflector watches a server and updates a store. That's like the second sentence in this Go doc. I don't know what a reflector is. I don't actually know what a store is either. And it kind of goes on from there. So the first thing we know, package cache is client-side caching mechanism. Store is a generic object storage interface. And there's a queue. There's something publicly exported from this package called a queue, which is exactly like a store, but it has a pop method. There's also a heap. And there's this thing called a reflector, which watches a specified resources and causes all changes to be reflected in a store. Sounds like we're getting a little warmer here. There's a config object, which contains all the settings for a controller. There's no documentation for controller. I actually don't know what a cache controller is, having read the whole package. It's not like a Kubernetes controller, so it's something else. Anyway, but keeping moving on, there's this thing called an indexer. And oh, hey, an indexer is a storage interface that lets you list objects using multiple indexing functions. Sounds good. And the description of new indexer is that it returns an indexer implemented simply with a map and a lock. So this is very similar to what I was just doing on my own, but I can probably use the cache package to do it. But I don't really know how to use new indexer. So at this point, new scavenging tool, grep, I will search the Kubernetes codebase to see where they're building new indexers. And it turns out not very many places are using this, and that should have been assigned to me, but I went with it anyway. The kubelet, however, which is a very fundamental part of Kubernetes, is using new indexer. And I feel like if it's good enough for the kubelet, it'll probably work for us. So we can kind of pull up the kubelet implementation, which this is where it's using new indexer. I am not going to talk through this because I'll just show you how we can change our script to work like it does for the kubelet. So that brings us to our third approach, which is the cache indexer approach. So in this case, when you create a new indexer, you need an indexing function. An indexing function really just takes an object of a certain type and then returns the index for that object. So I can create a function that says index pods by IP, and all it really has to do is return the pod's IP address. And then I can pass that to these primitives in the cache package, and everything should just work. So here we go. The first thing I do is I create my indexer, and I pass it my index pods by IP function. And then the next thing I have to create is this thing called a list watcher, and that takes the API client that we built, a resource type to watch, and the fields and sort of attributes that you want to watch on those resources. And then with the list watcher, you have to create a reflector, and the reflector takes the list watcher and the indexer and smashes them together, and then you can run it. So then the next thing to do is to run the reflector, and the reflector will actually tell you if it's fully synced with the Kubernetes API. So this is better than the previous approach because we can just, after we start the reflector, kind of keep polling to see if the reflector has been updated. And let's see. And then when we're ready, we just proceed, and then we can find the IP. OK, this approach is a little confusing, right? These are a lot of objects that don't seem to fit together very well. And I don't know, it works. This is how we did it in Linkerd for a very long time because we weren't really understanding how the package worked. And then one day it all clicked because I was watching Joe Beta on TGI Kates, which is this Friday podcast thing where he tries different things. And he was writing a Kubernetes controller, and he started to use this thing called shared informers. And I my jaw dropped, and I was like, this is what we need. So we can look at this is from his project where he's using informers. And he has a couple of really nice things here that we were not previously doing in our example. One is he has a new config or die method, which means you don't have to error check anymore. It'll just panic and exit. So we can use that in our script. And then you create this new shared informer factory. And then the factory will give you informers that will inform on certain types of resources, such as secrets or namespaces in this example. OK, so since we're almost out of time, we will just run quickly through the shared informer approach to see if this works for us. So we have a couple. The new hotness here is that we call new config or die. We create our shared informer factory, and then we grab a pod informer. And with that pod informer, we're able to add an indexer that takes the index by IP function that we created in the last example. And then we can start the shared informers. And then there's another utility that we discovered through watching the podcast, which is they actually have a function that will just wait until the cache is synced. So I don't have to do any of the manual polling or sleeping or anything like that. Like, you can just wait, and then it will sync, and then the script will proceed. And then when you're ready to find a pod by IP, you retrieve its index and then retrieve it by IP, and then you're done. And I'm going to give that one the 3 heart eyes approach. Still seems a little complicated, but once you sort of get the hang of using shared informers, they're kind of used throughout the Kubernetes codebase. There's tons of examples, like most of the controllers use these. And this is kind of the more canonical way of doing something like this when you're working with the codebase. But it was kind of a journey to get here, which is why I wanted to come here and tell you about it. And let me just give you the bonus loot from this section. Here we go. So the other thing is that once you're using shared informers, those are configurable. And so you can make some pretty sweeping changes with like very few lines of code. So like one thing you might want to do is watch only the pods in one namespace instead of all namespaces. In the previous examples, that would have been a lot more code, but you can just configure the shared informer factory to only produce informers that will inform on a single namespace. So it's valuable. We actually had to do that in our code base. And the other thing is you get a lot of test support, right? So you can build a shared informer factory from a fake client that's stubbed out with some test data. And then you can really test this stuff well. Yeah, so anyway, that's kind of the pods by IP part. That's all the code I'm going to put up on the screen for now. Hopefully it was bearable. I just want to go over a couple quick things, and then we will wrap up. Yeah, so got some information on both of the projects. I gave you a very poor description of how the Kubernetes project is laid out, and then we dug through a bunch of the code. And we used some cool tools of the trade. And yeah, this is just a single slide of things that might help, but don't take these as gospel. One thing is that there is information out there online about some of this. It's kind of spread far and wide, but if you're willing to take the time, that might be easier than just jumping headfirst into a large code base. Although if you're willing to do that, I don't discourage you from doing it. Reusable examples. So like many of the projects that have spawned from Kubernetes have an examples directory and have examples. It would be great if every single Go library had an examples directory that people could reference for, and it has kind of the canonical examples of how to use this thing. And then, yeah, documentation. Godoc can be kind of hard. I like Godoc for programming, for lower level programming. I don't know if it really gives us the space to give these higher level descriptions of how it all fits together. And so, yeah, I would like to kind of come up with better ways to communicate that. And then smaller packages. This one's very controversial. I don't know if everything needs to be in smaller packages, but I do think that something like the cache package being broken up into 5 or 6 packages would probably help with separation of concerns. So anyway, that's it. I put my contact info up here. Again, Kevin, I work for Buoyant. We are hiring Go developers, and I brought some Linkerd merchandise, which you can grab. Feel free to come up and talk to me about any of this stuff. Cool. And I think I went right up against the time, so possibly no question. Oh, okay. Okay, cool. I thought I was out of time, but we can do it. Do you want this mic? Okay.
This is kind of a silly question, but the new configure die, is that like basically a panic if it doesn't?
Yeah,
succeed?
yeah.
Okay.
If you look at the implementation, it just panics, like when the error, which is actually really appropriate for a script, right? So it's less code, but yeah, it's just a panic. Yeah.
talking of tools of the trade, do you use an IDE or do you just do everything in VI?
That's a really...
And then another quick question after that.
That's a good question. So when I write Go, I typically use VS Code, and it's nice to be able to drill down into menus. But I tend to use grep a lot more often for like larger projects because I kind of want to see all the use cases. Like sometimes I want to just go to implementation, and that's great. And then other times it's like, show me lots of examples and stuff like that.
So VS Code search you don't like too much?
I don't ever use search in VS Code. I'm a command line grepper at heart. That's what I do.
And then the second question is, when you're looking for code and trying to understand a new code base, do you ever use Panic, where you actually insert panics to look at the whole stack trace?
Yeah, so that works well as long as you're, if you're, I feel like that works less well maybe in the Go modules world now because it's harder to modify your dependencies because you're not all working off of one source tree. But yeah, that can often be a good approach, yeah. So, cool. Okay, all right, well, thank you, everybody. Appreciate it.
All right, thanks. So we've got Jack Zampolin from Tendermint and Cosmos talking about consensus and distributed and decentralized.
Yeah, absolutely. Ken, thank you very much for the introduction. Awesome. Well, as Ken said, my name's Jack Zampolin. I'm the director of product at Cosmos Tendermint. And just a little bit about me, like who's up here talking to you about distributed consensus. I initially had a degree in financial accounting, but ended up starting to program online, did a boot camp. My introduction to Go was with a company called Influx Data. We made a distributed time series database specifically focused on monitoring applications. And then worked there for a couple of years. And the first blockchain job I had was at a company called Blockstack. And I was there for a while, and I work at a company called Cosmos now. And I'm going to talk a little bit more about what we do. Just a quick show of hands, how many folks are familiar with or interested in blockchains in this room? All right, good about half. So probably going to cover some material that some folks are familiar with, but here we go. So why do we need distributed consensus in the first place? It's kind of a problem to get a bunch of computers to agree that x equals 5. If we're thinking about this naively, how would we go about it? First way to do it might be to rsync it. So, just copy the data manually from one computer to another. That quickly becomes untenable as the size of the data and the frequency of the updates becomes more than you can do. So maybe you want to do an active-active setup where you're writing to 2 different data stores at the same time. But what happens if one of those data stores goes offline and those nodes get out of sync? Maybe active-passive is better, so only one node is accepting writes and they're mirroring them over to another server. This might work if you've got very high uptime, but eventually you're going to get inconsistencies between the data stores. So we need something better. We need a better way to do this. Luckily, there's been a lot of research in this area, and there's a number of algorithms that allow us to get a bunch of computers to agree with each other. So there was a lot of research back in the 80s, and one of the first productionized consensus algorithms is called Paxos. So that was first published in 1989. It's broadly used inside of large tech companies and banks. And the really nice thing about it is it works. The computers agree. But it's kind of complicated. And one of the major issues with it is you have to trust all of the computers that are running this consensus algorithm. So if I'm running all the nodes, that works great. And it can give me these very high uptime guarantees. And that's why big tech companies and folks who need these persistent data stores really like Paxos and why it's widely deployed. But if me and everyone in this room wanted to keep x equals 5 in consensus, any one of us could bring down the whole cluster or start cheating, and that's not that great if you want to run a distributed database with a bunch of friends. Also, failure recovery in Paxos. I don't know if anyone's ever tried to recover a Paxos cluster. I have a bit more experience with Raft. But it's not great, and there's a lot of very manual tooling to do that. So in Go, if you're looking for a Paxos implementation to kind of dig into and figure out how Paxos consensus works, there's a number of them out there. This is one that's really commonly implemented as a part of many PhD programs. So you'll see a lot of Paxos implementations with a few stars on GitHub. But that's kind of the first and most widely deployed consensus algorithm. Next is Bitcoin. So what is Bitcoin? It's a cryptocurrency that holds a bunch of data in consensus. And the Bitcoin white paper came out in 2009. Everyone's kind of familiar with Bitcoin. And proof of work consensus, which is kind of the fundamental base of it, or Nakamoto consensus, is broadly used in a ton of different cryptocurrencies. Now, this has almost the opposite set of features of Paxos. So with Paxos, if we all tried to run it, someone could easily cheat. But with Bitcoin, it's designed so that we could all run computers and contribute to this consensus and ensure that it's secure and no one's cheating the algorithm. And this makes it extremely secure against adversarial behavior. But that's kind of where the benefits of this taper off. One of the really bad things is it creates this arms race-like incentive. And we're seeing folks out in the world create these gigantic server farms that are taking up all of the energy from hydroelectric jams in China. And there's tons of energy and money being spent to outcompete other members of this consensus group. It's very energy efficient, and it leads to this kind of winner-take-all security model, i.e. whoever has the ability to create the most nodes and hash power on this network is going to end up controlling it. One of the really cool things about the cryptocurrency community for Gophers is there's excellent implementations of proof of work consensus in Go. If you check out BTCD, this is a full implementation of the Bitcoin protocol in Go. Another excellent one is GoCoin. And the packages in those repos, you can just dig through them and see how it works. It's pretty simple. The computers compete to see who can do the most CPU work, and whichever one does adds transactions or data to the ledger. So what's next? The next consensus algorithm to kind of come into broad use is something called Raft. And this came about in 2013. It's in search of an understandable consensus algorithm, if anyone's interested in reading the paper. And this is broadly used in a number of open source projects like Kubernetes. So Kubernetes itself, in order to understand where all the pods run on the different machines, what network ingresses and egresses exist, and all of the other data that you need to keep track of in a Kubernetes cluster, you can't just hold that on one machine. Or else, if that one machine goes down, your whole cluster goes down. So you need some sort of distributed consensus to keep that data. One of the really nice things about Raft is it's easy to understand and it's easy to implement. If you want to go check that out, go check out the HashiCorp Raft implementation. And then that bottom link down there is from the Secret Lives of Data, which is by this engineer, Ben Johnson, who's the author of BoltDB. And that's a visualization of step-by-step how Raft consensus works. And basically, in Raft, the different nodes in the network elect one of the nodes as a leader, and all of the writes and updates to the ledger go through the leader, and the leader replicates the log to the rest of the machines. Now, this is great. It's much less complicated than Paxos. It's a little bit faster. But again, we need to trust the computers which are running this consensus. And it's limited to a relatively small number of consensus participants. You can run Raft clusters of up to 50 to 100 nodes, but scaling beyond that becomes slightly problematic. Also, again, failure recovery here. If you've ever tried to recover an etcd cluster, the tooling's gotten a lot better in the last few years, but it's still not great. So how would we run something like Paxos or Raft with everybody in this room and still be able to trust it? Because in Kubernetes, you could have, if somebody gets into the pod, one of the pods that's running etcd, they could bring your whole cluster down. So if we wanted to add additional robustness to Kubernetes, we would need something that doesn't have that property. So this is the family called PBFT protocols, or Practical Byzantine Fault Tolerance. And the first one of these to be kind of broadly available and used in a number of projects is called Tendermint. And the white paper, if anyone's interested in reading it, is Tendermint, Consensus Without Mining. And that came out in 2014. And it's used in a large number of blockchain projects. So the nice things about Tendermint are that it's understandable and implementable. It's much like Raft in that way. In Raft, leader election happens very infrequently. And one of the big differences with Tendermint is that leader election happens every consensus round, i.e. every time new data is added to state, there's a leader election as a part of that. This supports untrusted consensus participants, which is kind of what we want if we want to run databases with a bunch of our friends. And it allows construction of incentivization mechanisms on top of it. So if you want to gate access to your cluster, you might want to treat different traffic in different ways, and there's the ability to add sort of rate limiting and essentially through the use of cryptocurrencies on top of it. The bad part about this is it doesn't support an arbitrarily large number of participants. The current implementation goes up to around 300 participants. With a few different optimizations, we could get it up to the 3,000 range. And performance. You know, Raft is definitely a little bit faster because they're not electing leaders every round. There's fewer rounds in the consensus. Now, Tendermint is a Go project. So if you're interested in seeing an implementation of this in Go, you can go to github.com/tendermint/tendermint and check that out. And very similar to Ben Johnson's visualization of Raft, there's a visualization of Tendermint out there written by one of our engineers, Anton Klankov. And that's it right there. So if you're looking to use a distributed database for your project, what are some of the trade-offs you might want to think about? One of the first ones is latency versus security. So just for example, if you're choosing between, let's say, Paxos and Tendermint, Paxos implementations are highly optimized for write throughput as well as read throughput. And, well, read throughput's much easier because there's all the nodes, but write throughput's what we really care about. And the latency in Paxos is going to be much lower for writes than it is in Tendermint. But Tendermint gives you these additional security guarantees where if somebody gets into one of your nodes, they can't bring down the whole cluster. Another one might be permissioned versus permissionless. And in this example, maybe permissioned would be something like Raft. You have to give people permission to join the cluster and run nodes. Whereas with Bitcoin or proof of work consensus, it's permissionless. Anyone on the public internet that can route to the cluster can join it. Another one might be centralized versus decentralized, which is kind of this permissionless versus permission versus permissionless as well. In Bitcoin, the proof of work miners are spread out all over the world and anyone can join. This leads to this very decentralized agreement mechanism. Whereas if you're running something like Tendermint, which is PBFT, it's a little bit more centralized than that because you can only have around 300 nodes at this point. Another thing that you might want to think about is probabilistic finality versus kind of instant finality. In Bitcoin and proof of work, because of the way consensus works, there's a chance that state additions might be overwritten by future additions to the chain. That chance decreases with the amount of time those state transitions have been added to the chain. So it takes a while for you to be sure that your transactions that you've added are going to exist as part of the canonical chain. You can imagine this presents a ton of distributed systems problems, and if you want to transfer data between two proof of work chains, there's a lot of latency there. With Tendermint and some of the other PBFT databases and next generation blockchain platforms, they have finality, i.e. just like Raft. So when data goes in, if the database says that it's written and accepted into the consensus, it is final. So what's next? There's a lot of very exciting consensus research happening right now, a lot of it in the blockchain space, and a lot of it's happening in Go. If you see what's going on with Ethereum 2.0 and Polkadot and Tendermint Cosmos, where I work, there's a lot of effort going into building these decentralized systems where anyone can run these nodes and trying to push the boundaries of decentralization, making these systems run more and more nodes and pushing responsibility out to these node operators. And if you look at Facebook and Libra, there's a lot of large tech companies also contributing to this research. So there's a ton of exciting research happening, and a lot of it in Go. And that's kind of my talk. I want to keep a bunch of time open for questions. So if anyone has questions about any of the consensus algorithms or anything in the blockchain world in Go specifically, I'd love to answer them. We are hiring. This is my Twitter. And if you want some more info, go check us out at cosmos.network. Thank you, guys.
So in terms of uses for consensus algorithms, you got databases and message queues distributed. And that's one example. Yes. And maybe you can go through some examples of why that's needed. But then also you've got blockchain where you've got untrusted nodes in a public mainnet like Ethereum or Bitcoin, or you got a private permissioned blockchain or sidechain. Can you give other examples? Can you go through those examples of sort of why, what consensus algorithms are used and why, as well as then other use cases for other technologies?
Absolutely. So distributed databases and message queues, you'll see predominantly Paxos and Raft-based consensus algorithms used in those implementations. And when we were talking about trade-offs a little bit earlier, that's kind of that latency versus security. With a message queue for an internal system, you're kind of assuming that no one has access to it, and you're gating it with a bunch of security on your endpoints. Now, in these public cryptocurrency networks like Bitcoin or Ethereum, what you want to be able to do is allow anyone in this room to come join up to the network, independently verify the correctness and security of it, and download all the data and then be able to transact with it. And that requires something much more like a Nakamoto consensus, or a lot of the next generation platforms are using things like PBFT. Now, if you wanted to build a distributed message queue that anyone could join, you could build one with Tendermint or on top of Bitcoin. And what are kind of applications for that? You know, I think we're just kind of starting to see this with the ability to like transfer data between different cryptocurrency networks. One of the things that you can do with Tendermint is, because it's easy to verify the correctness of the chain, like i.e. that this group of nodes has been following the rules of the network for over 3 weeks. All of the data in the database rolls up to one hash proof. And you can transfer data between these different clusters. I'm fucking that up. Sorry, Ken. Did I answer most of your question there?
I think so, but just other than database and message queues, IoT devices, or are there sort of other areas where consensus algorithms maybe open it up to other people in the audience?
Well, a lot of the initial research was done in the aerospace and space field. And this was, if you've got an airplane that's got a bunch of different computers on it, let's say one of the wings gets popped off, you still need those computers to be able to talk to each other and agree on what the state of the airplane is. Bit flips in space is another reason why a lot of these protocols were developed. If you've got a computer and you're bringing it up kind of a little bit less shielded out of the Earth's atmosphere, it's very easy for cosmic rays to flip bits and mess with the data in your computer. And having a bunch of computers that agree helps mitigate that. So any area where there's mission critical data, and if one of the hosts goes down, that's where you're going to need distributed consensus. And then at that point, it's all about threat models and recoverability. Yeah. Awesome. Any other questions? Yes.
So this all comes with a certain dodgy reputation in some ways.
Yes, it does.
So I'm interested, that we've had other technologies where there's been fundamental research that has sort of altered the way the technology is used over time. Are there things with academic rigor being undertaken in order to improve these algorithms, and where is this going?
Yeah, absolutely. That's a great question. I mean, Tendermint itself, we're currently in the process of formally verifying it. There's been quite a lot of academic work on PBFT protocols recently, especially because of the recent cryptocurrency boom. MIT, Carnegie Mellon, Stanford all have tenured blockchain chairs, and most of those folks are doing consensus research. So the academic field has definitely gotten into this in a big way, and they're focusing on things like formal verification and improvements to protocols like Tendermint. So one of the things that you can do with Tendermint, which is what Facebook did, is I mentioned that every round you're electing a proposer. So there's a few different rounds where you're electing that proposer. I think Tendermint consensus consists of, I think, around 5 rounds, and the first 3 are proposer election, and then the last 2 are adding state to the database. One thing you can do is start electing the proposer for the next round in the first 3 rounds of the consensus algorithm. That's something called pipelining. So applying optimizations to these consensus algorithms to improve performance and some of the security guarantees they offer as well. And all of that work is predominantly academic. You're not seeing that. I mean, you will see that in kind of the Ethereum ecosystem. There was a ton of money that got pumped in there, and it's basically provided room for a lot of folks to spend time doing fundamental research on consensus algorithms and peer-to-peer networks. So does that answer your question? Awesome, great. Yes?
So where does latency come in terms of either the algorithms or just the timing aspects? So yeah, where does latency come in terms of?
Yeah, for sure. I think that most folks in this room are familiar with trying to get latency down under the human observability threshold of around 200 milliseconds. In the blockchain world, we are way slower than that. I mean, in Bitcoin, it takes about 10 minutes for a block to be confirmed. Tendermint, in a lot of the PBFT algorithms that are out now, you're seeing block times of around 5 seconds down to around 1 second. But in order to get these to be real-time systems, you need to get down below that latency threshold and ensure that users can make these updates and it feels like a modern system that they're using. In Bitcoin, I don't know if anyone's tried it, you like submit the transaction and then you're like, did it get in there? Like you got to wait for a bunch of time. So those kind of interactions drive users away, and the research to reduce latency, I think, especially in the blockchain space, is predominantly to bring the technology to a point where average users on a mobile phone can create transactions and have the kind of user experience that you're looking for in a traditional web application. Did that answer your question there, Ken?
Is it, for example, if you're doing a distributed database and you've got different geolocations, part of the latency would be because of the transmission across.
Yeah, absolutely.
Part of it could be the data packets that are involved. Part of it could be, and that you've got to write, and you've got to write to, and then get acknowledgement that has been committed. Part of it could be that from Bitcoin is that you've got the transaction has to get into the queue or into the block, and it may be waiting outside the block because you didn't pay enough gas or what have you. So I kind of wanted to go through what are some of the, whether it's a Raft or whether it's a PBFT, where the different elements of the latency might come in.
Yeah, so in Raft, each of the nodes has a key that it signs, and it says, I'm this node, I'm saying that this state transition is valid. So the nodes have to gossip those signatures to each other and ensure that all of the other nodes have signed off on it, it looks good. So especially as cluster size grows, you can imagine the number of those signatures grows fairly large. It grows linearly. So there's a lot of latency involved in that. And reducing the size of the data packets between nodes, that's a huge effort. One technology that's looking very promising right now is some cryptography called BLS signatures, and it's the ability to essentially concatenate a large number of signatures into one smaller signature and then do the same inclusion proofs, like i.e. say, is this validator included in this signature? And you can easily prove that. So that's one way that these protocols are going to reduce latency. I mentioned pipelining, which is just in the consensus algorithm, the ability to elect the proposer for the next round and make it much faster. There's a lot of research at the peer-to-peer layer. There's a company called Protocol Labs that is working on a project called libp2p. If anyone's familiar with networking, this would be using Google's Quick protocol, which is UDP over the internet, and it has connection semantics, which is kind of nice. So there's a lot of areas of research where latency is being reduced there. Did I get to that? Awesome. Ken, thank you. Any other questions?
Just a question about if there's any protocols that you know that allow you to reasonably reverse like a transaction?
The whole thing about blockchains is that once the transaction gets accepted, it's immutable. You can, and especially for large cryptocurrency networks, that's kind of a necessary property. You can build these systems where you can roll back these state transitions with sort of a operator key. You know, if you create some way where the creators of the system can roll back transactions, but that's a centralization vector. And I think one of the major reasons why you can't roll the transactions back is because the only way to do that would be through some mechanism like a kind of a pseudo mode in the blockchain. One potential way to do it would be to have a quorum of specific nodes that could roll back transactions based on a broad-based vote. But there's not a lot of folks that are kind of developing things like that right now. Awesome. Well, thank you all very much, and Gophers.
Thank you. Awesome. Appreciate it. Thank you.